what I'm doing here, I'm not celebrating Peter, because you're going to see Peter at work this in this work that I'm doing myself, actually to sort of close our joint research project that I was following in NYU when I met Pasquale, by the way. So the idea is, the title is funny. The idea is actually to intrude in a very old discussion between information theorists on one side and economists on the other side. So neither I nor Peter have been involved, at least as far as I know. Peter has made a lot of stuff, but he didn't consider himself an expert in investment theory. Okay, and so when I visited him, we decided to do investment theory. Neither of the two was actually in the field, and we ran into this very old discussion. It was an interest in Kelly rule, old discussion going back to the 70s, 60s actually, and even before, between information theorists on one side and economists on the other side. By the way, I was aware of Kelly rule at the time, but I didn't know very much the history of this fight between these two disciplines. At the beginning of the history of investment theory. On one side, at the time, there was Kelly, Shannon, Bryman, so very Thorpe that I'm going to use today, very big names of information theory that were saying, well, if you bet sequentially by reinvesting your profit and losses from now to a very long period of time, then what matters is the low large number. So you just have to understand that if you are reinvesting, you take the log on of your return each and every day, and you, if you want to maximize the average return, you don't have to bring any discussion about any assumption about your risk preference, because in the end the low large number will prevail. Okay, and so this was the point of view of information theorists. On the other side, we had economists, particularly Samuelson, that was had his own model with the power utility that is the only class of utility function which is myopic, so you can maximize period by period. That actually said, no, this is you're missing something here. You're missing risk. You have risk also in the long, in the very long run, and so you are missing a parameter that is my parameter of risk aversion, the parameter you have in the standard model. And the discussion was very, very harsh, particularly from economists to information theories. Merton on the same side. Markowitz was actually in the middle. Markowitz in 76 wrote a paper on Journal of Finance on this topic, and he actually proved that using his model, if you repeat the game, in the end, apart from a technical requirement on a function that he uses, actually the log wins. So the lowest number is prevailing. Okay, and so these were the two problems involved. Is it lowest number? Is it risk? Okay, risk aversion, propension to risk. Okay. Now, behind this, we were addressing the problem. Actually, curiously, we went to this by first we did the mathematical part, and then we found the model. We found that the model was corresponding to this. So we didn't start with this question. The question actually came up very naturally at the end. Our question was, is this true for any kind of dynamics? So is it true, for example, for the geometric Brownian motion or the variance gamma? Does it make a difference in the long run? This is the question that we address and solve in a paper that we published, unfortunately, in the issue in honor of Peter. Following this, I had a lot of discussion with colleagues, students, other people involved. Of course, with some of them were quite skeptic on whether a solved discussion, so consolidated result like the log utility maximization, the log wealth maximization, which even economics now as a number, growth optimal portfolio. So it's something that is a registered trademark, right? So is it possible that there's something missing here? There's something new to be discovered, and is it possible that is what we find, that this is true, the Kelly rule is true only for geometric Brownian motion, so only for log normal return. So I had a lot of discussion on this, even because we are involved with giants. Okay, so Bryman, Shannon, Samuelson. So we are, and after we wrote the paper, we received a lot of congratulations on one side, but as newcomers to the field. So Peter would forward the congratulations to me, or the criticism. For example, Steve Aston didn't like this for some reason, even because this question is continuing. This fight is continuing also today, where the information theories are not involved, but a group of physicists is involved that make a group based in London called ergodicity economics. That the fight is continuing on that field. Okay. So in the end, discussing with that, last Christmas I was in a call with a PhD student from Northwestern that was interested in this, but was skeptical. So was saying that I don't believe that the Kelly rule doesn't work. The Kelly rule is fully general. You only need independent return, not any specific assumption about the distribution. So in the end, I said, look, okay. Go on with the standard Kelly rule, and maybe our model can tell you something on what happens to you if you follow the Kelly rule, and the process is, for example, variance gamma. Okay. While I was doing this, I remember an old paper that I just looked through at the beginning of this project by Thorpe that was asking exactly the same question on the Kelly rule, saying you don't want to use the Kelly rule. That's what happens if you don't. Okay, you have ruin beyond this point. You have growing wealth below this. Okay, and so I said, well, I remake this paper completely. Okay, by using a variance gamma or another time change model. Okay, so these time change models, they allow us to cover at least the class of semi-matrix for which, as we're going to see, a moment generating function is defined. Okay, so what I'm doing is motivating by saying a little words on Kelly and Thorpe. That is what I'm going to use. Then I'm introducing the long-term investment with the time change by using variance gamma as the reference model, and then I will. I think with this paper I most likely close the door on this project, but there is another door that is opening, because in some way there is some uncertainty coming into the long run, and this uncertainty has to do with the distribution and the dynamics of the clock that you are using. So in the long run, you still have a model risk and estimation risk, remembering so sampling risk, remembering the words by Nassim Taleb yesterday. Okay, you have stochasticity. So on this side, we went with this paper. I give I give an argument in favor of what Samuelson will say. What about the risk? Okay, and the answer is, in the long term, you don't have risk. You have uncertainty in an item sense. You don't know the model, or you don't. You have to estimate a parameter, which is basically the variance of the clock. Okay, that's the point. Okay, so let me briefly start with the basics of the Kelly rule, that in the end are very easy, because you have compounding. So in the end, when I arrived, Peter, why don't we study compounding? Okay, if there is only a compounding rule, which is the geometric compounding rule up there. If there is that geometric compounding rule, then of course, if you ask what is the average growth rate, well, you take the log, right? So you take the log, and what Kelly actually says in the end, in the conclusion of this paper, I don't care about utility function. I know this for Norman Morgenstern is coming out right now. Good luck, but I'm not dealing with that. I'm just saying that if you take the log, since you are reinvesting, well, the low large number applies to the log. Okay, and that's why you have to maximize the log. Okay, so this is the point. Okay, so if you do this, this is the standard, the first example in Kelly and also in the Thorpe paper. So you have a Bernoulli model with probability of success P and probability of failure Q. You run, you invest, you have €1, you invest a percentage F constant every run. Okay, and you have to maximize. You have to maximize the growth rate, which is by the low large number that is inside there. By the low large number, you have to maximize G with respect to F. You get the famous Kelly rule. If you plug the Kelly rule behind inside the objective function, you get minus the Shannon entropy plus log 2. Okay, that's the model. Okay, now the key to our discussion is this function G. Okay, there was another paper. This is a paper that I rediscovered following my discussion with a PhD student. Thorpe published a paper in '69. Okay, saying redefining the probability of ruin. Okay, of course, in the model, in the Kelly's model, you don't have the probability of reaching zero is zero. Okay, you cannot reach the boundary, so the ruin cannot happen. But you may redefine the ruin in an almost sure sense, which is what Thorpe did in this paper of 1969, and then he made an example applied to the stock market 20 years later, and what it does is that you draw as a function. So bet how much you want between 0 and 1. Okay, but you know that by this function, you know that if you have the region where this is negative, you will have ruin almost sure. Okay, meaning for every positive level you may choose, you go down to the level with probability 1. Okay, so you have a boundary region here, and so you may ask yourself, well, I don't want to use the Kelly rule, which is the maximum here, but I can bet any amount in this region. I will be safe because maybe I'm going to arrive at the optimal a little later, but I'm heading in the good direction. If I instead invest in this region, okay, then I will get to zero almost surely in the new definition of ruin. Okay, so it is natural now for me. My task was to apply the same question to this model. Say you use the Kelly rule that so you invest this, okay, and the G function is not like this. It's something else that I'm going to show you. Okay, then are you still safe in the no bankruptcy and no ruin region? Okay, that's the question. Okay, so and this brings me to the idea that to the paper that we wrote with Peter. So in the Kelly rule, we have this structure here. We have a log return. We have a non-stochastic time, calendar time equal to business time. We have non-stochastic time. Okay, we change this by assuming that this time here is stochastic and has a gamma distribution or inverse Gaussian distribution, some distribution. Then you see here that the return, if you now you have to integrate out. You have to take the expectation across all the possible realization of the business time. And if you do that, you get the moment generating function evaluated at the sk, which is the log return. Okay, this is the idea. So we get this new function here. This is the moment generating function that keep track of the distribution of the distribution of the stochastic clock. Okay, So let me now extend this to a multi-period investment. So we have we have a period running from 0 to 1. We assume n reinvestment. Okay, so we partition the period into n sub-period, and for each sub-period we have a different we have an IID stochastic clock in the unit time, which that add to to a random variable which has expectation equal to n. Okay, if I assume that I rebalance, for example, every year. Okay, otherwise the data T is the same. Okay, now another issue that was raised by this time by a guy from the industry that wasn't able to wanted to simulate this but didn't manage, was the fact that we are using this representation here. So the growth of the random variable, which is the growth of the wealth from 0 to time n, because capital T is equal to n here, is the exponential of the average log return times a random variable now, but in this case it's the realization of a random variable, tau n, which is the business time after 20 years, for example, if n is 20. Okay, and so we had a lot of discussion with many people, but including this colleague, on how to define this S, how to simulate this. Okay, and the simulation maybe is the next paper on this figure. However, the point is that here I prove that we trivially that if you assume that this covariance is final or is 0, which is I assume. So between this variable S and Z, then I can write this the growth of my wealth in this way. Okay, and this is the starting point of the proof that was made actually by Peter, so here you see Peter at work. I was about to go back to Italy 2 days before, and we had a meeting on Marshall-Hawking, on the Marshall-Hawking derivation of Archimedean copulas, which is basically a tool that we saw in this conference 2 days ago. Is simply the mixing of two random variables, the mixing of two random variables. So I was aware of that working on copula. It was, and then I explained this to Peter. The problem being ever was that you integrate with respect to a single variable, not a path or a sequence of a random variable. And in the copula function, you have the same variable across the board, and so it's easy to get to do this. So what the day after at 8:30, I was in the office. I received a mail by Peter with this proof. Okay, so I said, "Well, you didn't sleep tonight." No, I woke up early, and this is mine, and so he gave this proof, which is an application of the Marshall-Hawking structure of proof that you find in JASA 87 for copula functions, applied to a problem in which the variable is not, you don't have a single variable. You have a variable which is a sum of n independent variable. And what do we get? I gave you briefly the proof. It's very easy, but it's quite, it's from a genius, particularly someone that learned about Marshall-Hawking approach the day before. So it's, you substitute here the sum. These are independent, so you take the product. These are IID, identically distributed, so you take the product of these, and you, of course, have to assume that they have a moment-generating function. And so in the end, you have the moment-generating function of a linear sum of logarithm. Okay, and you may rewrite these because this is the way you write an Archimedean copula, basically. Okay, so you rewrite these in Archimedean copula. You don't have n on the denominator. You have 1 on the denominator. You get this formula, which looks like the formula of an Archimedean copula, but it's something else. It's because we were referring to the same paper when I arrived. We saw a paper by Maslow that was quoting this result on Kolmogorov average. Okay, so Kolmogorov defined a set of axioms by which an average is called regular. Okay, good property from an average, and he has a theorem that says that if you have a generator which is monotonic and you build you compute these, then you get an average which satisfies the axiom of the regular average. So what we found was a geometric average, okay, which is actually, if you allow for stochastic clock, which is actually a Kolmogorov average with the generator corresponding to the moment generating function of the clock, okay, of the clock at unit time. What is most important from my paper here is that is to observe that if you want to get to the linear form to which the low large number applies, okay, now you cannot take the log here. Okay, you cannot take the log of this. Okay, you just have to apply. You just have to apply the inverse of the moment generating function to the expected effect, and then you get something to which the low large number applies. Okay. So, in which case do you get the Kelly result? When this inverse psi is the log, okay, which is when the variance of the clock is 0. Okay, this is the result that we are claiming. Okay, so from this you can now you can introduce a model. The best model you may introduce is the variance gamma here, because there's a lot of interesting, similarities and connections, interactions with some other kind of research, because you see here, if you take the gamma clock with the unit expected value, that this is the moment generating function, this is the inverse, and this is actually a power function that reminds of the power function that was advocated by Samuelson. But the point is that in this case, the the power part, the meaning of this parameter gamma here or theta here is that this is the variance of the clock. Okay, this is the variance of the clock. Okay, if the variance of the clock goes to 0, you get the log. Okay, you get the log. You get the s per here, and you get the log. You get the log here. Okay. Now you may rewrite these by, of course, variance has to be positive. You may rewrite these in this by switching by switching the sign. And then you find another connection, which is a connection with the Savi's algebra, which is used in physics. Okay, Savi's redesigned a new algebra to study non-extensive dynamics in physics, and the starting point is to write the exponential in this way, the log in this way, and then you get the product, which is this, and you get the sum, which is this. Notice that the product is the Clayton copula. Okay, so when I discovered this, and a co-author of mine was visiting Rio de Janeiro, where Savi is working. So you gotta go to discuss with Savi. He was not aware of copula, so he called all their co-author, and my co-authors, Sabrina Buinacci, had to give a lecture on copula in this department. By the way, this also has a name. This is called Sugeno fuzzy measure in fuzzy measure theory. So using the gamma is a crossroad of very many brings you to physics, fuzzy engineering, of course, option pricing, which is what we are interested in here.
I have a question straight away.
Yeah.
Very quickly. What can you make this if instead of using the gamma distribution, you modify x with an exponent between 0 and 1, so you put an alpha there, and you get into the territory of the so-called Mittag-Leffler-Linnik type distribution, which are essentially fat-tailed modification of the gamma. So things are no longer exponential.
I can do. This is the example that I'm making because it's the most famous one. Okay, yes. You can play around with this a lot. You can also change it, as I'm going to see.
Yes, I think it's compatible with the fact that very straightforward tail modification.
Yeah, you must conserve a moment-generating final moment-generating.
In which case, probably not. Okay. But you can recover it somewhere.
Okay, that's the point. Okay. However, you maximize, if you want to get the maximum, you maximize just like you do in the log, and you get these answer. But this is not the point here, because I want to do torp here. I want to answer the question. If you stick to Kelly, but the word is variance gamma, what happens? Okay, and what happens is here. Okay, here I use a theta, a variance of the clock equal to 0.5, and you see that the region is below here. Okay, so if you have the optimal Kelly bet, where we are still in the same region. Okay, maybe you arrive later, but an interesting point that also only for the variance gamma model is that if there is a point, if you set the variance of the clock to 1, then you get that maximizing Kelly, you are exactly at the boundary of the ruin. Okay, so you are exactly separating, but it's I tried with other models. It's only a property of the variance gamma. So if you plug 1 there, then you have that the boundary is exactly corresponding to the Kelly betting. So if you are betting, if you are betting with the Kelly rule optimally, and the variance of the clock is 1, then you are exactly on the ruin boundary. Okay. Okay, then this is again the simplest example, the binomial example. Then Thorpe makes 2 other examples. One for the stock market, which is important because we introduce leverage. Okay, and I use that, and then a third one with the stock market with estimates. But this is is something I'm going to make in the future when I'm looking for a co-author to work on this. Okay, so Thorpe made another example of uniform distribution of the stock market between a lower bound and an upper bound. Okay, in the paper they are specified at different level. So I extended this. In this case, you would have instead of the function, you will have the log of the function up there. Okay, so I computed the maximum, the optimal point as Thorpe did, and obtained this formula here. I mean, this is important for me because then I'm going to show you what happens with actual numbers you find in the market. Okay, but these again the same structure as before, the same schedule before by using theta equal to 0.5 and the Thorpe model of equity. Okay, now. So this is quite. This I guess answer the question that was raised by the PhD student that was talking to when I talk of this paper. Now, but this raises thinking a little more of what we've done here. And so the question is, so what's new between maybe you can bet Kelly and you are lucky and you are in the region. Maybe you are not. What is the difference between these 2 models? Well, there are 2 striking differences. Difference 1 in the Kelly-Thorpe model, the function is log. Okay, that's it. No parameter involved. Okay. In the CC Cherubini model, many families, I mean, infinite families of distribution and function and log function. Let me call them pseudo log function inverse psi can be found. So from one model to the other, you have plenty of room for model risk in this setting. So model risk, point number 1. Point number 2, estimation risk. Even if you believe in the variance gamma, you have to estimate the variance of the clock. Okay, what you get is an estimate. Okay, so are you sure that it's the true estimate? How large is your sampling error? And this was the point raised on other the stochasticity of this function. Okay, and well, this is an example of model risk. I take variance of the clock 0.5, and I use the variance gamma and the inverse Gaussian model. Okay, you see the results are very different. Okay, variance gamma is much more disrupting in a sense. Okay, so which model to use makes a lot of difference. Okay, the point is that just to reiterate, the point is that if you were in a non-stochastic clock model, you would be absolutely here on this line. If you are not, if you are in a stochastic clock model, here you have not only one distribution, a set of distributions that can bring you in any place, but always below the original Kelly frontier. Okay. So model risk, number one. Estimation risk, number two. Here I collected some estimates for the parameter theta. Okay, so this is Madan Karen Chen estimate. Okay, these are interesting because these are estimates made by Platten and others in the 90s, with and without the crash of the 87. So you see sort of a difference between these two. These are same market, but one estimated by Platten and another by Seneta that used compared maximum likelihood estimation with method of moments estimation. And so here, even here, you have some difference. And I don't report here the result that you find for the Nikkei market, in which the variance is above 1. So it's something that takes you to the ruin. Okay, and here I computed the boundary. Okay, important thing that Thorpe says, Rotando and Thorpe in the paper said, look, here we allow for leverage. Okay, leverage, never-ending leverage. So you from now to infinite, you borrow. You may borrow up to 17% of your wealth to reinvest it, and you are still in the safe region. Okay. Look, that if you allow for stochasticity of the clock, you see that to be safe, you better stick to 70% of investment in the risky asset. Okay, because otherwise, already at 66, you can get your risk being in the ruin region. Okay, so it seems that in a more involved, in a more complex world in which you don't only have a stochastic dynamics, then you typically you see the leverage is not allowed if you want to if you want to avoid the ruin. So leverage forever is not allowed. Okay. Now let me. So these, I think, as I said, closes the door on this project, unless you, destroy it now. Okay. Okay. And so, but it opens another door. So, what about choosing the right distribution and the right parameters for the stochastic clock? And this brings me to directly to Cherny and Madan and the idea of acceptable risk. This is still a conjecture, meaning that I didn't I didn't have time to make the math to see whether, as in the Cherny and Madan paper, I get from the acceptability index to the distortion. Okay, but if I can, then a possible new element to be studied is the acceptable average growth rate over the long run, in which I have a set of possible moment generating function from a set of probability applied to the stochastic clock. Okay, if the link acceptability index distortion works, there is an interesting result from my co-author Sabrina Mulinacci and a PhD student of her that makes it's about a distortion of moment generating function. Okay, and a specific case in which the distortion actually from the probability goes directly to the distortion of the moment generating function. One of these is the gamma. Okay, and so possibly for some distribution, for cluster distribution, you could actually have this. So you have a distortion, okay, of a moment generating function, and and that will give you the geometric growth rate to get the growth rate to which the law of Lagrange number apply. You take the inverse of this. So you get the inverse of psi G applied to S. Okay, and that's the end of the story for now. Okay, so just summarizing. The approach, we assume IID stochastic clock dynamics. Okay, we observe and we prove. Peter proved, even though he was saying, "This is your paper." I was quite angry. Your paper. You made the proof. Okay, so our paper. Okay, in our paper we prove that generally you average geometric returns are Kolmogorov means in which the generator is the moment generating function of the stochastic clock. Okay, here we prove that the novelty is that as I told this PhD student, most likely if you bet Kelly, generally you bet too much. Okay, which is what we prove. You bet too much. You risk going into the ruin region, because the ruin threshold is lower. Okay, and the result for the standard Kelly result, hold only if you have log normal returns. Okay, that's the point. Now, so not IID, any IID return, only if you have log normal returns. Okay, then this open the new door on risk on long-term investment. In this sense, we provide an argument to Samuelson. Okay, Samuelson, there is risk in the long run. Okay, but it's not on the Sharpe ratio. I happen to discuss a PhD thesis that they're going to discuss next week, which was a guy that was actually simulating the return over 50 years, was reporting the Sharpe ratio was 600, a little bit. Okay, well, because the volatility goes to zero. Okay, so you don't have risk, you have uncertainty. You know, you may be you may land on any possible schedule of a torp generated by a different clock. Okay, and then you have, of course, estimation risk. The open door now is to prove and open the door on whether there is a possibility for acceptable average growth rate leading to distortion of money generating function.
Thank you very much, Umberto. Questions? Please.
I was just wondering, like, did he simulate this model in particular?
What?
You were mentioning you were just simulating this model.
Yeah.
He managed to do that in particular when he found out with this result about 600.
The practitioner didn't believe in no, I didn't understand the question. Maybe a little loud.
That your PhD student or like one of them.
Yeah.
Okay, so did he manage like to simulate this model in particular?
No, the Kelly model. This is the whole story. They didn't believe in. They didn't believe in this. Okay, in this model here. Okay. They said, well, I take the log. Since they are IID, I take the log. I will still have the geometric compounding. Okay, so it works. It works until they are IID. Okay, but the point is that so the answer to this is that okay, if you do that, you may end up here, or here, or down here, or here. Okay, so you have a distribution across the possible result that you may have, and if you compute the average return, you cannot avoid an actor, which is in all the statistical theory we call the diabolic misnature. Okay, the diabolic misnature is selecting the model and the distribution that you have of this result. The distribution is like this, but for some reason the average is always below. Okay.
Billy? Was Billy first?
Oh, okay.
Just a couple of comments. One is that some models that look at returns in the long run, basically there are these papers by Farmer and whatnot of how kurtosis in actual data stays alive till up to 40 years. And most of these models have kurtosis disappearing because they are IID and they're Levy. And so I've looked at models that build a temporal fractional Levy structure, and those models keep high levels of kurtosis in perpetuity.
Mm-hmm.
And they are also closer to the data, what we have to know from the data.
Mm-hmm.
And so the question is, how one would approach the situation when we ensure that the higher moments are not disappearing in the long run.
Yeah,
which over here they are. That's one comment.
Yeah.
The other comment is that I see this business of looking at the long run, as I've commented in my talk also, as looking at the long run as something that you can eat, okay? Because if you're not going to be here for that long run, and you're not going to eat it, And really, all you can hope to do is in the span of time, your run is like 5 minutes, okay? The strategy can run for infinity, but you're going to run for 5 minutes, okay? And so what happens at the end of 5 minutes is that you have to sell the strategy back to the market, okay? And when you sell the strategy back to the market will then say, okay, I'm going to apply a conservative valuation to this, and that's where the infimum of measures comes in. The infimum of measures at the end is basically trying to capture what is the financial value of the strategy and not the benefit of eating it, because you're not here to eat it. So those are the 2 comments.
Well, very well taken comment. To the first one, I told you I ran into your paper with Eberlein that actually does what you mentioned. But you have a set of process, and you in this case you will partition my Z into some delta Z n and another Z at okay.
Okay, that's one way of doing it.
But it's something.
Yeah.
But the point here is that this Cn makes the return not, as far as I see, not independent anymore, right? Because this is still there for several.
No, for the steady thing, it will be additive process. So they're independent but not homogeneous.
Not stationary.
Yeah, not stationary. But in the tempered fractional Levy process construction, they are stationary. And
so I guess until this as a moment generating function, you do this on the subordinated process. I'm doing this on the subordinated, right? But until this as a moment generating function, this is something that add to the model risk that was saying before. The second point is that what you're saying, you have to close in the market. For some reason, in this literature, it's proved that. I also again refer to this PhD student that I'm going to discuss next week. That even if you have information, or if you play around, in the end, in the long run, at some point, and the fixed strategy prevails. Okay, it's better. So at some point, the information is no longer something which is strange. Of course, I agree with you that I'm gonna die sooner or later. So I will have to. It will be important to estimate this in finite, but large but finite time. And I guess that your model with Eberlein is the best candidate for this.
Well, among other things, but another remark was that instead of variance gamma, if you use variance gamma makes the variance of time for up moves and down moves identical. And if you use bilateral gamma, you get 2 variances, one for the up moves and one for the down moves.
Yeah,
and so you get 2 parameters that go into the clock.
I get the product of 2 Kolmogorov averages.
Right.
Basically, that's.
And so you'll have a richer dynamics in terms of what's
that's a natural.
What's happening to your Riemann region? With respect to if you increase the variance of down moves or you increase the variance of up moves, which one? Which one is doing what?
Definitely something to be considered, and not mostly in the applied in the application, or maybe in this version.
Yeah.
I have a question regarding with the Kolmogorov aperture. So, in a step formula, you definitely need your characteristic, your moment generating function.
Yeah.
Or is there not any way to extend it to if you have only a characteristic, for the transport characteristic function, or do you really need the moment generating?
No, here I need the moment generating function because I'm computing the average growth rate. So in the end, I must have a closed form, or no, I must have a well-defined moment generating function. So for the case in which you have a characteristic function but you don't have a moment generating function, you can apply this.
You can or Laplace transform, which is
a question is whether in this case coincide with, for example, non-existence of moments or something that they're very specific, in which, of course, this business, of course, so to get the perimeter of when these work, because as you say, a moment generating function must exist. Okay, so a condition under which the moment generating function, general condition under which moment generating function doesn't exist, rule out this. For sure, they don't exist if you have a case, for example, I guess, right?
Yeah, but you can, there are some papers by Castagnoli, 73, 74. You can essentially define a generalized characteristic functions that takes the generator inside, and you can take that actually.
Okay, so there's a potential perhaps of in my views, what I'm looking into is one way of generating this persistent, as they say, persistent skewness, persistent moment, persistent implied volatility skew, is to use as a subordinator a non-Markovian process, which is
wait a minute, not what I'm doing
it's
here.
not so much about the Markov property. That's not the point. The point is if you have an inverse in time, then you can. So if you don't have Levy subordination, that's the point. If you subordinate it to the inverse of a Levy process, which is what we would call a subfusion, then what you get is actually this phenomenon of persistence at the moment in the long run.
Okay, I take note and maybe discuss. But it's not. I mean, it's not about finding a new. So the problem here is saying that when all the world says that there is just one Kelvin rule, the best you can do in this Kelvin rule. Here the message is no. You have a Kelvin rule only if there is a log normal model. Otherwise, your return is going to be lower, and your probability of doing higher. That's the point.